Hello everyone watching online, which is both the people watching live and the people watching in the future. It's semester 1 2020 and the things going on this year, if you're watching from the future, mean that that's why I'm in my room and not at university. And we're doing this on Zoom. It's a revision seminar for Maths 1M and I'll be talking through the things that people have requested. Okay. Right. So requests I've had a mathematical induction and some stuff on the techniques of integration. So I'll talk about those, and if there's time, I can talk about other things. I'm going to say up front, you can always drop into the Maths Learning Centre. This semester, it's only available online. There is a special My Uni course, which I sent a link to all of you for, that you can log into. Most of the time, at the moment during exams, the tutors just have an open Zoom session you can jump into. Otherwise, you can put your question on the discussion board and they can chat to you about that at the time. We're open 10 AM to 4 PM Monday to Friday. Okay, cool. I've got another request that involves some vector stuff, but I'll see what I can get to. All right. So first I'm going to have a chat about mathematical induction. So, right. Induction is, in the history of mathematics, a really important kind of proof. When the mathematicians in the 1920s to 60s, even earlier in the 100 years up to the 1950s, went back and filled in all of the technical details that made mathematics consistent and logical, one of the things they did was use mathematical induction. So you can construct all of the mathematics that works on whole numbers from 3 axioms, which are there is 0, every number has a number after it, and mathematical induction. And together with that, you can create all of the mathematics that exists on whole numbers. I mean, not really, because it takes a very long time to do it, but theoretically you can. And so that's why mathematical induction is so important to pure mathematicians. But also it's like the gold standard for proving anything to do with whole numbers. I know that in computer science, when you do proofs involving the speed of algorithms and how long they take and how many operations are involved, you use mathematical induction for that, because an algorithm counts how many times something happens in a certain situation. Sorry, when you have an algorithm that works on a certain size of number, you can use induction to prove how long it takes. Okay, so that's why it's important. So I guess I'll write that down. I'm not going to be able to give you my notes, I'm sorry, because I'm working from home. So if you want me to stop so you can write something down, just let me know. Using induction. Okay, so that's why we think it's important. And the idea of it is that we create a machine that does the proof for us. So mathematical induction is quite different to other kinds of proof. There are kinds of proof like direct proof where you can just say, start with some assumptions, do some logical steps, blah, 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 and end with a conclusion, and that's great. What mathematical induction does is it takes one of those and does it in such a way that you can reuse it over and over and over. So this is how I imagine mathematical induction in my head. I think, well, there's like the number 1, 2, 3, 4, 5, and so on, forever. And what we have is we create a machine. So there are things that we can say about these numbers. So the idea is that there's a thing you can say, this is a speech bubble, about the number 1, and it's either true or it's false. And there's a thing that you can say about the number 2, and it's either true or it's false. And there's a thing that you can say about the number 3, and it's either true or it's false. Oh, that's a much better speech bubble. Okay, so there's all these things that you might say about these numbers, and they're either true or they're false, each one. And so what we're going to do is we're going to create a machine, a proof machine, that will take a statement about a number being true, like this, do some sort of argument and produce the answer that the next one is true. And so what's going to happen is, if you know it's true at a particular spot, then you can go, oh, cool, that's true. My machine will take the fact that that's true and pass it over to the next one. And so number 2 is going to be true as well. And then the machine will take the truth of it being true at 2, pass it over to the truth at 3. And so it will know that 3 is true as well. And the machine will take the fact it's true at 3, pass that over, and it'll be true at 4 as well. And we can just let the machine run itself on each answer until where it can be sure it's true for everything. But the way that the system works is it has to be true somewhere, and once it's true somewhere, it's going to be true for the one after that, and the one after that, and the one after that, and the one after that. But the part of mathematical induction that we're interested in is this part here, which is the bit that we have to construct. We have to construct an argument that will take any number in, do some sort of working, and like a statement about a particular number, do some sort of working and produce a statement about the next number. That's what we want to do. And so that's how induction works. So that's one way that I have of thinking about it, that you've got a machine that passes its information from one to the next. But it only works if the thing that you put in is true. So you need a thing that starts. And I have like a statement like that says true for n equals k, and it goes into the machine, and the machine does its work, and it spits out true for n equals k plus 1. So you say, well, it's true for this particular value, spits out true for the next one. That's the idea. And it doesn't really matter what order you do these things in. Yeah. So what you need is some sort of system that transfers how to get from one number to the next number. That's the key to this. Figuring out whether it's true for any one specific number is not going to help you figure out how to do this. You need to look at two numbers next to each other and see how they're related in order to do it. Okay. So I just had a question that I need some people to help me answer. Can we figure out some common situations in which during this course you have been asked to do inductions? So in the tutorials or in the lectures, I want to figure out what sorts of induction questions we've had, because they tend to require slightly different sorts of reasoning. While you're thinking of that, I'm going to go and see if I can search for some as well. So I'll give you just a couple of minutes to maybe look through your notes or just think about this. See if you can come up with some sorts of induction, things that you've had to prove using induction. Okay, so, oh, thank you. I'll just have a look at them. Okay. Cool, thank you. I can see a couple of the sorts of things that we can do. For people who've been putting things in the chat. So thank you. Oh, interesting. But there's some very different sorts of things. All right. Cool. Did you want me to go through some of those ones? Live? They're very hard to come up with off the top of my head. Yeah, okay, cool. So what we're going to do is I'm going to go through them. We're going to try and have a look at the sorts of reasoning that we can repeat when we do these sorts of problems. The three that I've been given are quite different to each other, and so that's really good. We can see how they're similar and how they're different. Okay. So the first one was not that one. Oh, yeah. So I'll just do an example. So let x be greater than or equal to 1. Prove that 1 plus x to the power of n is greater than 1 plus n times x for n greater than or equal to 2. Okay. It's as clear as it's going to get, I'm sorry. Okay. So, right. So the first thing I would be doing when I'm looking for something involving something involving, yeah. When I'm looking at something that I'm trying to prove, if it involves an integer or a whole number somewhere, and I'm supposed to prove it for all whole numbers from some point forwards, then that's when induction is useful. So if you can turn your problem into something about integers somehow, then you have a chance of proving it by induction. So this number x, I can't use induction. I can't change the number x to the various different options x could be using induction, because x could be any real number. So it'd be 1.00001 or 3.857201647, whatever, and then the rest of the digits of pi or something. I can't use it for that. But I could use it here where this n is an integer. So that's something I could do. So in order to investigate this, it's a natural instinct to try it for each value of n to see if you can see that it's true for each, and that's fine, but it won't tell you how to do the proof. The only way to know how to do the proof is to figure out how you get from one number to the next. So you could, if you wanted to, try it for a couple of numbers and see if you can reuse one of them to figure out the next, and that will tell you how to do the algebra to do the next. Or you can just straight up try the algebra to begin with, which is usually a little quicker. And if you're in an exam, well, speed's going to be important. So I'm going to try it just with the algebra first and see how that goes. So let's see. I want to prove that this is greater than 1 plus nx for various values of n, starting at n equals 2. I need it to be true somewhere. I need it to be true for the first one in order to use induction to get to the rest. So what I'll do is first I'll show that it's true for n greater than or equal to 2. Sorry, for n equals 2. Welcome. I'm just writing the document camera. If you want to make it bigger, you can hover over it and pin the video. We're talking about induction at the moment. Okay, so let's see. 1 plus x squared is 1 plus 2x plus x squared. Okay. And well, there's the 1 plus 2x. That would be what I get here, the 1 plus 2x. So x, well, if x is greater than 1, then this is definitely more than 0. Okay, so that's greater than 1 plus 2x, since x is greater than 0. And so therefore it's true. Cool, it's true for n equals 2. All right, so induction would allow me to find a machine that will allow a statement like it's true for n equals 2 to be turned into a statement true for n equals 3. And it would also, that machine would turn a statement true for n equals 3 into true for n equals 4, and so on forever. And so we believe that it was always true for any number we cared to think of. So what we need to do is we need to create a little proof that supposes that it's true somewhere and does calculations to get it being true for the next one. So let's suppose it's true for n equals some unknown but specific value of k. So I'm just supposing it's true for one value of k because my machine has to start somewhere to get to the next one. And so that would mean that we're supposing that 1 plus x to the k is in fact greater than 1 plus kx for all x greater than 1, I guess, technically. Okay, so somehow we have to use this fact to prove the next one. So what we want to be true is this, but with a k plus 1 in these positions. So it seems to me that it might be easier to begin with this. Let's consider, I'm telling the reader to think about this, to the k plus 1. And we want to do some working that eventually declares that this is greater than 1 plus k plus 1x. So I know where I'm headed. I'm just going to write it on the page, just softly, because I might have to rub it out. That's where I'm going. Okay, first I just want to check if everyone's okay with what I'm doing at the moment, or has anything to say, or any questions at the moment.
I sort of have a question.
Yeah.
And let me just 1 second, sorry. Can you explain Euler's method?
Okay, that's a whole separate thing, but I'll add it to my list, okay?
Sure.
I might not have time for it because there's already requests about induction and integration and some vector things, but I'll see what I can get up to. If I don't, you can always drop into the Maths Learning Centre virtual drop-in centre and ask there later, okay?
Sure, awesome, no problem.
All right, cool. So here we are with our induction. We know what we're aiming to do. We're trying to connect these two together, and we need to be sure that this is greater than this. And somehow we have to use this fact because that's the only thing that we've assumed to be true. It has to start with this information to pass it on to the next number. So it seems to me if I can find one or the other of these in here, preferably this one because I'm trying to head forwards, then that'd be good. And I can do that because this is the same as 1 plus x to the k plus 1 to the k times 1 plus x. So that's good. All right. Now, we know that 1 plus x to the power of k is definitely more than 1 plus kx because we just said that. So this is going to be greater than 1 plus kx times 1 plus x. Okay. Don't know what's going to happen next. So I'm just going to expand it out because I can't think of anything good at the moment. So this thing here is equal to, that equal to just refers to the one directly above it, not to this one up here. Just so you know, that's how lots of mathematicians write these sorts of chains of reasoning. So 1 times 1 is 1, 1 times x is x, k times kx times 1 is kx, and kx times x is kx squared. Okay. Oh, look, that's the k plus 1x. That's 1x plus kx, which is k plus 1 lots of x. And kx squared, actually, we've used reasoning like this before, back here when we did this one. We noticed that that bit had to be positive. And so since this is bigger than 0, this thing has to be bigger than that. Okay, so we've done it. We've created a machine. Oh, just a second. Therefore, true for n equals k plus 1. So we've created a machine that starts with suppose true for n equals k, does some stuff, and concludes n equals k plus 1. So no matter what number this k is, if we know it's true for k equals 2, blah, 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 therefore true for 3. If we know it's true for 3, da, 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 therefore true for 4. So this machine, if we let it run forever, will show that all of them are true. And so we can say, therefore, true for all n greater than or equal to 2 by induction. And that's how I would do this one by induction. So, any thoughts about what I've done here?
Sorry, yeah. On the last two steps, it seems like you've gone from the right-hand side of the equation, so on the inequality, it would be the 1 plus k plus 1x. So on the very last step of the whole process.
There.
Yeah, it seems like you've kind of, I don't know, maybe I just got lost there when you were doing it, but it seems like you've gone from the right-hand side of the inequality and then it switched back to the right-hand side. And I'm just
it became this side.
Yeah.
Yeah, so look, if I was trying to show that something was equal, right? Then I could go thing equals 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 and finish with the last one.
Yeah.
And that's what you'd normally expect if it was equals. And I'm just checking that you're worried about what happened when I had some of these greater than things in the middle.
Yeah, I kind of just got a bit lost with
So I'm just going to check something. Just going to check. If I had started by saying this to begin with, and I had worked on both sides of this inequality simultaneously, would you have felt better about that? Like where I did something like multiply them both by 1 plus x.
Yeah. Yeah, I mean, that would be fine.
Like that?
Because it's essentially the same thing.
Yeah. Okay. I'm just checking some things. So the key thing that makes this whole proof work is actually, I mean, there's this bit where I replace the 1 plus x to the k with something that I know it's greater than. That's important. But the other important bit is this bit here, which you can't see at all because it's in yellow. So the key moment in my proof here was noticing that this is a positive number, which means that whatever this number is, it's definitely more than the thing we were hoping for. So inequality reasoning is like that. You're allowed, like, if you want to show an inequality, the thing I wanted to show was this is greater than that. That's the thing I wanted to show. I have to turn this into something that I definitely know is greater than that. And that's what I did. I'm not sure how to explain at the moment. I can dig deeper into how you're thinking and feeling about that to try and resolve this issue, because I'm sure you're not the only one who feels this way. Inequality reasoning is a bit weird.
Yeah. I mean, because it looks like you, on the right-hand side, you expanded the brackets, which is fine.
Here?
So you ended up with 1 plus x, yeah, that one.
Yeah.
And then you simplified it so it looks like the original state it was in.
Yeah, except there was an extra bit. Yep.
Yeah, exactly, because of the 1 plus x multiplied it by. But then you compared that to it without it, and it just feels like you're kind of you're comparing two different things. I don't know. Yeah.
So yeah, so were you all right up to here?
Yeah, pretty much.
Okay.
Yeah.
And so you're wondering about this magic trick.
This is not something I would have ever picked to actually, be
Yeah.
a reasonable thing to state.
Yeah. So the first thing is that I'm not figuring anything out technically. I am just trying to make a statement about the numbers that are here. So this whole thing works out to some number. And so far I know that this number is less than that number. So this number is greater than this at the moment. All right.
Yep.
And so my goal is to make a statement about this that's greater than something. So if I know that this is greater than something, then I can say that this is greater than that other thing as well.
Okay. So if the 1 plus x to the k plus 1 is greater than that, and that is greater than the original thing,
yeah,
then it's true. So
that's right.
Yeah. Okay.
So because this is more than this and this is more than this, that means this is more than this.
Yeah.
So if I was going to be writing this properly, I probably should have put an intermediate conclusion and said, so therefore 1 plus x to the k plus 1 is definitely greater than this thing. So following this through, I've been able to make the conclusion that this thing has to be more than this thing.
Yeah.
So and then I can say therefore true for n equals k plus 1.
Okay, so the 1 plus x to the k plus 1 is greater than the 1 plus x plus 1 x plus kx squared, which is greater than 1 plus k plus 1 x. Okay, yeah, no, that makes a lot more sense.
So it'd be a little like saying, not that these numbers are correct, like a little like saying, well, 100 is equal to like 50 times 2, which is greater than 40 times 2, which is greater than 30, which is greater than 80, which is greater than 80, which is greater than 60, and so therefore 100 is greater than 60.
Yeah.
Something like that.
Yeah. Okay. Thank you.
Yeah.
Thank you so much. That actually makes a lot more sense.
Yeah, and that inequality reasoning is one of the things that makes these kinds of induction problems actually hard, because you've never had to do that before. You've never had to chain together several greater than signs when you're doing algebra before. And so it's normal to feel like, what the hell? And it also means that you don't come to this with strategies that are already useful. So this move where I just made something vanish and was able to say greater than, it's weird, like if you've only ever done equals. Because when you're doing equals, you're not allowed to do that. You can't just remove something. But in this case, if you remove something positive, it definitely gets smaller. And that's what we were hoping for, it to be smaller.
Yeah.
Thank you for asking that question. I'm sure that will be very helpful to everyone who's watching this.
Thank you.
You're welcome. So, how about try another one? Everyone okay with that? Well, at least one person has said they're okay. Okay. That thumbs up thing is new. That wasn't there in the last version of Zoom, so I'm very happy about that. I might even just start a whole new page. Okay. All right. Let me just see if I can find another example. Prove that the nth derivative, well, I might even make one up of my own. Just give me a moment. I'll do it off screen. Just give me a sec. Okay. It takes a while to figure these out. I just didn't want to do one that was actually in a practice exam in case people were waiting to try that. Tricky. Yeah, no, I won't do that one. All right, I think I've got one. All right. Got it. So we're going to prove that dn over dx to the n, so the nth derivative of x e to the x is x plus n times e to the x. Oh, actually, just a second. X plus n minus 1. Yep. Okay. For n greater than or equal to 0. So just in case you didn't know, the 0th derivative of a function is the original function, because you haven't done the derivative yet. Okay. So let's give it a go. So it has to be true for the first one, and I can't use induction to prove that. It has to be independently true, so I'm just going to have to show that. So d to the 0, x to the n, x e to the x is just the original function. Actually, do you know what? It's going to be easier if I give the function a name so that I don't have to keep rewriting everything. That f of x equal to e to the x e to the x. All right. Then we need to show that the nth derivative of x, don't know if you've ever seen this notation, it's a good one. If you put the number in brackets up here, it means it's the derivative, however many derivatives. So a brackets 1 would be the first derivative, a brackets 2 would be the second derivative, a brackets 3 would be the third derivative. Don't know if you've ever seen it, but it's a good one. I like it. Okay, that's what we need to show. I've just changed it so it's just a little easier for me to write. Okay, so let's show it's true for n equals 0. So the 0th derivative of any function is the original function, which is x e to the x. Cool. And x plus, oh no, it is n. Damn it. This is the problem with making up questions. Sorry. I was right all along. Sorry about that. Original question is it's x plus n e to the x. So x plus 0 e to the x is indeed x e to the x, and so they are in fact the same. Ta-da! Fabulous. Okay. Now I've actually sorted out what the question actually is. Gosh, that'd be a horrible exam. It's like, figure out what this question it has to be in order for this question to work. I had to do that in an assignment once when the lecturer had a typo, and that's what they changed the question to. What does this number have to be in order for this to work? All right, we've done that bit, and so now we have to do the bit with the machine. So suppose for n equals k, so the kth derivative of x is supposed to be x plus k times e to the x. Okay. Then I need to figure out what the next derivative is and show that it's x plus k plus 1 e to the x. So well, let's just do it. F k plus 1 x will be the derivative of the previous one, which is going to be the derivative of this. So I guess I have to use the product rule. The derivative of that is 1, because the k is a constant, so that'll go away. So 1, and I'll keep the e to the x. And then I'll keep the x plus k, and then I'll do the derivative of e to the x, which is e to the x. Now there's an e to the x in both of them, so if I pull that out, I'll get 1 plus x plus k, which is x plus k plus 1. Okay, so that's great. It's done. So true for n equals k plus 1. Therefore, f to the n x is x plus n e to the x for all n greater than or equal to 0 by induction. Thoughts or questions about this? It probably was a waste of time to do this in this notation, but you know, it just made me feel better. Easier than you expected it to be, right? Yeah, they often are. Things where it's equals tend to be a little easier than the greater than anyway. But yeah, so this is a cool way of doing integration by parts multiple times without having to actually do it. If you happen to have a formula that you think is true, you're supposed to prove it with induction. Yeah. All right. So that's cool. Let me try this other problem. What was this other one? Cool. I might just share the screen so I can read that. Was this from one of the assignments?
Yeah, that was from one of the weekly assignments.
Yeah. Oh, okay, so let's see. Let S0 be 1, S1 be 3, and for n greater than or equal to 2, Sn is Sn minus 1 plus 6 lots of Sn minus 2. Okay, so this is a recurrence relation. That's what I would know this as. And so we're saying that each number in this sequence is constructed from the ones before it. And they've done an example. So S2 is S1 plus 6S0, which is 3 plus 6, which is 9. S3 is S2 plus 6S1, which is 9 plus 18, which is 27. Pardon me. Okay. In fact, it appears to be the case that Sn is 3 to the power of n for every n integer n greater than or equal to 0. Prove this fact by induction. Using the inductive hypothesis. Well, I'm going to ignore that bit and do it by induction my own way. Oh, it's strong induction. Oh, I love strong induction. Okay, so let me just pause for a minute and talk about strong induction for a moment. So before I said that induction, I'll see if I can find it. Before I said induction, you create a machine that takes the fact that it's true for one number and uses it to get to the next number. But sometimes that doesn't work, and instead you make a machine that takes all the numbers so far and puts them all together to tell you that the next one is true. and that's called strong induction. Yeah. I don't know if your lecturer called it strong induction, but that's what I know it as. And so the machine actually gets bigger each time. But basically, you make a new machine that goes true for n equals 1 up to n equals k, or wherever it starts. It could be n equals 0 up to n equals k. And then it does its thing, and it produces true for n equals k plus 1. That's strong induction, and it's actually okay to use that when you need it. And the times when you'll need it is when the process that gets you from one number to the next involves the previous numbers. So in this particular question, the process that figures out what Sn is involves the numbers before it. And so that's what we're going to have to use this time. It doesn't, the process, you know, in the first problem that we did, the process that gets from, in this problem, the process that gets from 1 plus x to the n to 1 plus x to the n plus 1 is just multiplying by a single number. You don't have to use all the powers so far. And the process that got from one derivative to the next is to start with the one you've got and do a derivative. And so each one only requires you to know one thing. But if you need to know about more things than just the one before, then you need to use this strong induction thing. You don't have to. You can just modify it to use the 2 before or something like that. But this is what we've been told to do. So let's have a look at it again. I'm going to put it on the screen while I'm reading. Oops. Okay. So S0 is 1, S1 is 3, and for n greater than or equal to 2, you get Sn is Sn minus 1 plus 6 Sn minus 2. And the goal is to show that Sn is 3 to the power of n for n greater than or equal to 0. Okay. Okay. So we're probably going to have to check it for the first 2 because you need 2 of them to be true to be able to figure out what the next one is. So it's not going to be like normal induction because where there's only one thing you have to check. The first thing we need to check is we need to check as many as we need to make the next one true. So we know that when n is 0, S0 is 1. And 3 to the 0 is also 1, and so therefore S0 is 3 to the 0. And also, when n equals 1, S1 is 3, and 3 to the 1 is also 3, so therefore S1 is 3 to the 1. Okay, so therefore it's true for n equals 0 and n equals 1. All right. So then what we're going to do is we're going to suppose it's true for every number up to k, and then use any or all of those to prove the next one is true. It's not good grammar. I need to put a word there for. Okay, suppose true for n equals 0, 1, all the way up to k. Some k greater than or equal to 1. So we only suppose it's true for up to the last one that we happen to know is true. All right, cool. And then we're going to do some stuff and conclude that it's true for n equals k plus 1 as well. All right, so I'm not going to write down every one of these being true, but I mean, I could. So it'll be like that S0 is 3 to the 0, S1 is 3 to the 1, all the way up to SK is 3 to the K. That'll be fine. All those things have to be true in order for my argument to work. So now I need to figure out what happens with k plus 1. And I need it to be true eventually to equal to 3 to the power of k plus 1. That's the goal. All right. Well, there is one thing that I know, which is how Sn is constructed from the ones before it. So that's this formula here. So let's see. This would be sk plus 1 minus 1 plus 6 times sk plus 1 minus 2, which is sk plus 6sk minus 1. Okay. But I also know that sk is equal to 3 to the k, and sk minus 1 is equal to 3 to the k because it's true for everything up to 3 to the k minus 1 because it's true for everything up to k. So I'm just going to pop that in. So they're all true. So the sk is 3 to the power of k, and the sk minus 1 is 3 to the power of k minus 1. And somehow I have to get this to be equal to 3 to the power of k plus 1. I'm just going to look and see what's similar and different here. This is a 3 to the power of k. This is a 6 times 3 to the power of k minus 1. The 6 itself is a 2 times 3. Yeah, I reckon that's going to be useful. Because then this 3 times 3 to the k minus 1, that's 3 to the power of k. And now these both, we've got 1 lot of 3 to the power of k and 2 lots of 3 to the power of k. So that's 3 lots of 3 to the power of k. And then 3 times 3 to the power of k is 3 to the power of k plus 1. Okay, it worked. So therefore, sk is 3 to the power of k plus 1. So true for n equals k plus 1. So since it is true for n equals k plus 1, it's actually now true for everything up from 0 up to n equals k plus 1. And so we can reuse the machine. It's just a little bit bigger this time to get to the next one. Technically, we only need the 2 previous ones, but you know, we're just doing a bit of overkill. So therefore, Sn is 3 to the power of n for all n greater than or equal to 0 by strong induction. You don't have to put the word strong in, but you know, I feel better about it. All right, thoughts or questions about this, please? At the moment, thank you. So the times when you would want to use this is when the process that creates the thing uses more than one step. Or possibly just a previous, like one of the previous steps as opposed to all of them. So there is a classic in, so there's a classic in one of the computer science courses later that goes like, Tn is like 5 times Tn over 2, something like that. And so this one uses a previous one, but not the previous one. So it's easier to, if you wanted to find a formula for this, then you could, and then they'd say something like prove, you know, T of 1 is like 6. And then they'd say, you know, prove that T of n is less than, well, I think it's like 2 to the n or something. Maybe not that. Something like that. And it was a classic because you, I think you need a floor function here. Have you seen the floor function before? Anyway, the floor function rounds something down to the number below. And so what they would do is you would say that, crap, I was wrong. Anyway, it's not this. I'm trying to remember something. I think it was like actually a 2. But anyway, yeah. So you can use this, and you can use the fact that it's true for everything before, so therefore it's true for what you get when you divide it by 2. So there are some systems that use just one of the numbers before as opposed to the specific one before. So the person who asked originally, do you feel like you have some strategies for induction? If you're still here. Yes, you are. Good. I feel better for you. Induction is something that can feel a bit overwhelming. Yes, you will need to practice. I can also recommend to anyone with this that practice is good, but every time you practice, you need to stop and look at what you did to see how you got to the end so that you can reuse those strategies. One of the things we forget to do is to look back and say, what could we do next time? And another useful thing to do is that you can read existing working that does these things. And what you need to do is say, well, what strategies did they seem to be using? And can I reuse those? So it's not like you don't want to have a big list of all kinds of problems and a procedure to solve each one. But what you do want is some key moments where you're saying, oh, that was a good trick. They noticed that something was positive, and so therefore they can say it's greater than what it would be without it. Something like that was a strategy that I used. Yeah. All right. Let me have a chat about integration then. Oh, just before we move on though, I'm completely happy to keep talking about induction if people want to ask them another question about it, or anything I've said, or any other thing about induction. Cool. All right. If you think of something, just let me know. Okay. Man, this one's crap. It's not as good as the one in the lecture theatre. Okay. So let's just have a look at integration. And integration has 2 lives. One of its lives is definite integrals, which accumulate quantities across time or space, and so and if those quantities are negative, so when you accumulate negatives, the answers get smaller. So it turns out to be the same as the area between a graph and the x-axis, but only if you count the areas below the x-axis as negative. So that's one life. And the other life that integration has is the opposite of differentiation. And the techniques of integration go with that life, where you're trying to find the opposite of integration, opposite of differentiation, which would be great. Except differentiation is actually pretty cool, right? In terms of being able to do stuff. There's about 3 or 4 rules, and if you just do them, the answer comes out. And often it doesn't even matter which rule you use, it'll often come out the same answer every time. But, so what do we have for differentiation? For differentiation, we've got the product rule and the chain rule. Technically, the quotient rule is a combination of these 2. and all the other rules are what to do for specific functions like powers and e to the power x and that sort of thing. So that's great. But the problem with the product rule and the chain rule, like if we're trying to do integration, we try and do differentiation backwards. And the problem with the product rule and the chain rule is it can be quite difficult to tell when you look at something if it has been produced by the product rule and chain rule. So that can make it hard to do this stuff backwards. But the general idea in integration is that the reverse of the product rule is integration by parts. And the reverse of the chain rule is integration by substitution. That's the basic idea. They sort of go together like that. Yeah, but unfortunately, because integration is another operation backwards, that makes it harder. In the same way that division is harder than multiplication, well, integration by parts is harder than the product rule, and integration by substitution is harder than the chain rule. Also, it's not like these two things are exactly the opposite of these things. Integration by substitution is able to do more stuff than just reverse an existing chain rule answer. And integration by parts is able to do more stuff than just reverse an existing product rule answer. Just that's kind of the other thing. Okay, so before I even get into that, I think that so far you have learned technically 4 techniques of integration. And I'm going to list them for you. Okay. So technique 0, I call it 0 because it's the most fundamental one, is just do it. You happen to notice that the thing you have is the derivative of something that you know, and so you just write down the answer. So under the just do it category are things, I'm going to do some examples of this in a second, so I'll just skip to the next page. Under the just do it category are things like the integral of x cubed dx. And you go, oh, there's a straight up rule for that. Put the power up by 1, divide by the new power. Okay, that's just do it. Yay. I'm pretty sure you've done integrals of trig functions. Am I right about that? You've done derivatives of trig functions? Yep, cool. So the integral of sine x dx is, and you'd go, okay, so it's got to be cos. It's either plus cos or minus cos, and the derivative is plus cos, so it must be minus cos. Yay! You just write it down, whereby just you have to remember it or be able to look it up. Now, if you're in an exam situation that's essentially an open book exam, it is still useful to be able to remember the basics so you don't have to waste time looking them up. So I say to myself, it's got to be sine, cos, it's either plus or minus, and the derivative is plus, so the integral must be the other one. Okay. Cool. That's good to know. Interesting though. All right. And there is a second sort of technique of integration, which sort of, it's still part of the just do it one, and you're allowed to just do it without doing anything. If you see, so it sort of goes like this. So it's like, it's sort of just do it and a half. And I call it divide by the constant derivative. Sort of, yeah. And it goes like this. It goes, if you know that the integral of little f of x comes out to be some other function, big F of x, then you also know that f of like ax plus b is 1 over a f of ax, big F. Basically what I'm saying is that if you know what to do when it's just an x, and it's not an x, it's a constant x plus constant, you are allowed to just divide by that constant. You don't have to show any working when you do that kind of integral. And the reason it works is that if you differentiate this, then the a will come out and multiply by the 1 over a that's already there and give you that. So my example is I know what the integral of x cubed is. It's x to the 4 and it's a quarter. But it's not an x cubed, it's a 5x plus 7, so I have to divide by the 5. Ta-da! And sine of 2x. I know what the integral of sine is, it's minus cos. But it's a 2x, and so I have to divide by the 2. Ta-da! You're allowed to just do that. You don't have to. You don't have to do any working. You're allowed to just go straight for it. Yeah, it's so common that people don't care if you don't show working for that. And you need to be extremely careful. You're only allowed to do this trick if the thing that is inside is constant times x plus constant. If the derivative of the thing inside is a constant, that's the only time you're allowed to do this trick. All right, so that's including this. So technique 1 is to rewrite it. You might want to expand it out or factorize it or use a trig identity, some sort of algebra manipulation to turn it into something that you know what to do with. So, for example, integral of x squared plus 1 dx, x squared plus 1 then squared dx. My rule for just doing it isn't going to work because the thing that's inside, the derivative is 2x, and I'm not only allowed to do that, divide by the derivative trick, if the derivative is a constant. So I'm not allowed to do that. So I'm going to have to, well, maybe I'll expand it out. So I get x to the 4 plus 2 times x squared times 1 plus 1 squared, and that I do know how to integrate. 2 times a third of x cubed plus a half. No, well, 1 just goes up to x, doesn't it? Yay! So that's what I mean by rewrite it. Rewrite the thing you're about to integrate, and it might make it easier. So you might want to use some you know, some log laws or some trig identities. You know, this one, for example, it's one of my favorites, sin x cos x, because you can go, oh, there's a trig identity that's got sin x cos x. I know that that sine of 2x is 2 lots of sin x cos x. And so therefore a half of sine of 2x is sin x cos x. And so therefore the integral of sin x cos x dx is the integral of a half of sine 2x. So the half will still be there because it's multiplied on, and then the sine will go up to minus cos, and I'll divide by the 2. Ta-da! And just fit it on the page, a quarter of cos of 2x. No, there's no dx. I got rid of that ages ago. Okay. So far, thoughts or questions? Cool. So these are the techniques that you sort of already had before you learned anything special. And they're classics. The other two techniques are substitution and by parts. There are some other techniques that are specialized, but they're all based on these ideas. So there's one that you learn in Maths 1A, I think, which is called partial fractions, but it's really just a fancy way of rewriting things. And in Maths 1A, you also learn, or possibly Maths 1B, you learn trigonometric substitution, but it's just a fancy kind of substitution. Used to learn reduction formulas, which is just a fancy kind of by parts. So all the other techniques of integration in general are based on these four. The reason I've written them in this order is that this is the order you should try it. It's usually quickest to just do it if you already know the answer. And then if you can see a way to rewrite it, that usually is quicker than any of the others. And then you would try substitution, and only then after that you'd try it by parts. But you wouldn't necessarily try it really, like do the full working. You'd sort of have a look at what's there and have a think about how it might turn out. So the idea of substitution is that one part of it is the derivative of another part. It doesn't matter which bit is which. It's usually a part that's inside something else is a derivative. The part that's on the outside is a derivative of something that's on the inside. So part on the outside is the derivative of something on the inside. It doesn't have to be used in that situation. As long as there is some function that's inside some other function, then substitution can often help. And by parts is specifically for when there's two things multiplied together. But I will note that substitution also happens when things are multiplied together, because the thing on the outside, if there's two things multiplied together and one of those things is the derivative of the other, then substitution is the thing to use. So don't look at a multiplication and go, it must be by parts, because often it's, you can just expand it out or something like that. Okay, so the point of substitution is when you see one part of it that looks like another part, that looks like the derivative of another part. So this is a classic. So I would first look to see if I can just do it. And anything with a squared inside the cos, I've got no hope. If it was just x plus 1, then I might have a chance, but then the x out the front. Bleh. Okay, so I can't just do it. Rewriting it isn't going to help. That 3x is trapped outside. This is trapped inside the cos. This has got no way of interacting with the thing that's inside the cos. Cos just doesn't play that way. You can't bring things in and out of the brackets, so I can't rewrite it. So substitution is the thing that I should try. And the thing I should try with substitution is to see if the derivative of this is close to some other part. Which it is. The derivative of this is 2x, which is close to being 3x. It's only out by having a wrong constant, and that usually means it's going to work. So I would say let u be equal to x squared plus 1, which is the part that was inside something else. And then what I would need to do is I would need to replace everything that involves an x here, including the dx, with things involving u. So let's see, du on dx would be 2x, the 1 would disappear. Then I'm going to do something that sounds awful if you're familiar with how derivatives work, but I'm going to do this and split this up. Okay, because for the purposes of integration, that dx count is an extremely small movement along the x-axis, and this du is an extremely small movement along the new u-axis, because you're basically remarking your x-axis in terms of u instead. So we want to know that if you move a little bit along your x's as the numbers labeled in terms of x, how will that change how fast you're moving along the numbers labeled in terms of u? Now, I'm going to go looking for this in my function. I've got the dx there, it's all multiplied together. The 3x, it's not quite right. I've got a 2x, so I'm just going to adjust it. I'll divide by 2. And so the 3x must be 3 over 2. And so therefore, my integral so the 3x dx altogether, all of that together is 3 over 2 du. The cos is still a cos, and all of that is u. And so that's where I am. And so the 3 on 2 is multiplied on, so it'll still be there afterwards. Cos becomes sine, because when I differentiate it, it will be minus sine, yep. Plus c, and the u is really x squared plus 1. If I wanted to integrate this again, I wouldn't have any hope. I couldn't do it from here, because the only way to integrate something that's got an x squared inside it is to have an x on the outside. Right. So how are people feeling about that particular one?
It's easy while you're doing it, David.
Yeah, everything's easy when someone else is doing it. Okay, so are there situations where you're not, where you feel like you don't know what you're doing with substitution? Or well, just with integrals?
I think we covered substitution pretty well.
Mm-hmm. All right. So just to let you know, you can actually play around a bit with how substitution behaves. I'm just going to do one of my favorites. This is one of my favorites. The integral of x over root x plus 1. I have no idea in what situations this integral would appear, but integration to me is just a game. I don't have to be examined on it. And I think it's useful for you learning to play some of these games. This one I can do by substitution. There's all sorts of craziness going on here. There's two things that are inside something else. We've got an x in the top of this fraction. We've got a x plus 1 in the bottom of this fraction under a root sign. I definitely don't know how to just do this, and there is no way for me to rewrite this in a useful way, because I'm never going to, that x plus 1 is never going to escape that root in order to make it easier. I can't expand this out. I mean, I could try rewriting it as like x plus 1 to the minus a half. That's a possibility, but then this x on the outside is never going to be able to interact with these x's here. I'm just sort of stuffed. But substitution might help, because if it wasn't a plus 1 under that root, then I might possibly have a chance of rewriting it. So I'm going to do a substitution. Let u be x plus 1. And then du on dx is just 1, because that's the derivative of x, and the 1 becomes 0. So du is the same as dx, so that's great. So this dx can become a du. This x plus 1 can become a u. and then we've still got an x, but that's okay. As long as I write everything in terms of u, I'll be all right. U is x plus 1, so u minus 1 is what x is. So I've now found every piece of this and figured out what it is in terms of u. So the x is u minus 1. The x plus 1 is u, and this is du. And that one I can rewrite, because u divided by root u is root u. And 1 divided by root u is 1 over root u, and they're both powers of u. So this becomes u to the plus a half, and this is u to the minus a half, and I can integrate both of those. So power up by 1, so that'll go up to 1 and a half, which is 3 over 2, and then I'll divide by the new power, so that'll make it 2/3. Power up by 1, that'll go up to plus a half, and I'll divide by the half, the new power, which will give me a 2. And so I've got 2/3 of x plus 1 to the 3 over 2 minus 2x plus 1 to the half. Because that's what u was, wasn't it? X plus 1, yeah. So this is one of my favorites because it doesn't look like substitution would help, but substitution is the next thing on my list, so I just give it a go, and it actually turns out to work after all. The point of this story here, actually, for me, when I choose to tell this one, is that substitution doesn't always actually do the integral for you straight away. It just turns it into another integral that you're supposed to then use a different technique to figure out. So my substitution didn't turn my integral into one that I knew how to do, but it did turn my integral into one that I knew how to rewrite. So that's just an important thing. And sometimes you just have to give it a go and see how it turns out. Rightio. So what I'm going to do is, I know that I'm technically at the end of my time, but I'm just going to keep going because I want to finish this. What I want to do is I want to talk about integration by parts. Integration by parts is the last technique. Substitution overall is a little easier, mainly because it has less places to lose minus signs. And I know in myself that I'm extremely likely to lose a minus sign if there's one to lose. And so I don't like to do integration by parts. It took me years to remember integration by parts. I'm sure I remembered it during my first year maths exam, but that memory didn't last, and I had to keep relearning it. So there are two ways that people have of trying to remember integration by parts. So one of them, one way is to know that it's the reverse of the product rule. So what a lot of people are, can I ask your lecturer, do they use F and G or U and V when they do integration by parts? Cool, okay, that's what I use. So the product rule goes that FG, when you differentiate it, is F dash G plus FG dashed. And so then if I integrate everything, then I'll get the integral of FG dashed is just FG. I'll get this. And then I can move one of them to the other side. So if I move, say, this one to that side, I'll get, it'll be written the wrong way around. And so you start here and you can turn it into that. That's the product rule. It's written in reverse at the moment. And this is how I remembered this when I was in first year. I actually strongly remember deriving this during my exam because I couldn't remember the rules. But something that's worth noticing about what is written on the page here is that all three of these parts have an F times G. All three of them have an F times G. Two of them have integral signs. There's an integral sign at the beginning, there's an integral sign at the end, on the outside. And two of them have dashes, the same as the one with the integral signs. This one, the dash is on one of them, and this one, the dash is on the other. And it doesn't actually matter which one is which, as long as it switches when you move from one side to the other. So it could just as easily have been fg dash dx, f dash g dx. So it doesn't matter which one has the dash, as long as the other one has the dash on the other side. So when I write integration by parts, when I'm trying to do it, remember it from scratch instead of derive it, I write fg, fg, fg. One has a dash here, the other one has a dash here, and then there's integral signs like that. That's how I remember it. That might not help everybody. My memory skills tend to work a little differently to quite a few other people, but sometimes it helps people to know that. Yeah. Okay, that's the thing. So integration by parts is designed specially for functions that are multiplied together that the substitution doesn't help for. So have you done the derivative of ln x in this course?
Isn't it 1 over x?
Yep, cool, good. I just wanted to make sure it was here. All right, that's not going to be relevant yet, but I just wanted to point it out. Let me do this one. The integral of x cos 3x. So I'd first try my things. If there was no x, I'd know what to do. I could just use my divide by the constant derivative rule. There is an x, so I don't know what to do. There is something inside the cos, so I could try and use substitution, but if u was like 3x, then I'd still end up with a u on the outside because it wouldn't be taken away by the derivative because the derivative doesn't have an x in it. So this x is still going to be floating around afterwards. And so even if I did a substitution, it would still have a u times cos of u eventually. So substitution is not going to help. So by parts is the next thing to try. And it is two things multiplied together, so I'm onto a good run. So this is how I would normally write the working for this. I'm going to say this is f times g. So this one's f, this one's g, and one of them will have a dash and the other one won't. So you have some decisions to make about which one is the one that has the dash. And the decisions are made on the fact that when you do this, it's going to come out to be this. Okay, that's how integration by parts works. The fg dx becomes an fg minus an integral involving fg. But one has a dash here and the other one has a dash here. So one of them is going to be differentiated by the time we get to the end. And we would like it to be something that we know what to do with by the time we get here. The derivative of x is 1, and a 1 times isn't going to make a difference to what's happening here. So I think I should differentiate that x. So I should get an f dashed at the end. And so this one's going to have to have a dash here. That's how I make my decision. So technically all part of this line should be telling the reader what f and g stand for. So f is x and g dashed is cos of 3x. All right, so I'm going to need f dashed, which is 1. And I'm going to need g, which is the integral of cos. So the integral of cos is sine. I was just about to write the integral of cos is cos. Hearing me. And because of the 3 there, I'm going to have to do that. The reason I've written it this way is that in my head, integration is down. Sorry, differentiation is down and integration is up. So I tend to have to arrange things on the page that way, but it might be easier for you to write f and g dashed and then f dashed and g, whatever. It's just, you can put it on the page in whatever order you like. And so now the f is x, the g is 1/3 of sine of 3x. The f dashed is 1, the g is 1/3 of sine of 3x. And now here we are. I'll just write it a bit more cleanly. So just like with substitution, it doesn't do the integral for you. It just turns it into another integral that you're supposed to then do. All right, the 1/3 is multiplied on, so it'll still be there. The integral of sine is minus cos. And the 3x means I'm going to have to divide by 3 again. Okay, so we get 1/3 of x sine 3x minus, there's a minus minus, so to make it a plus, 1/9 of cos 3x. Whew. That's integration by parts. So you will notice a couple of things I did, hopefully, a couple of things I did there to stop myself from getting things wrong. And one of them was putting a big pair of brackets around here, which stopped me from losing this minus sign. Any questions or comments about that particular one that I just did, which I reckon I can fit all on the one screen? Cool. Some lecturers are able to skip this bit in the middle and go straight to here. I don't do integration by parts often enough to be able to do that. So I always write the FG, 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 and write this bit down and sub everything in. It just makes it a little easier for me. I do want to show you one classic trick because I have one page to go that is fun and useful with integration by parts. Integration by parts is used when things are multiplied together, and sometimes you can't see the thing that's been multiplied together. Well, let me just do this. The integral of ln of x. Okay, so here's the thing. I don't know how to integrate the ln of x. I know how to differentiate it. The derivative is 1/x. But the integral, I don't know. And I can't rewrite it. Ln of x is never going to get any simpler. It is what it is. And substitution, well, there's nothing inside it. There's nothing to substitute. So there is literally nothing I can do. So by parts is the only strategy I have left. And the only way to do by parts is to have two things multiplied together, which I don't have. But I can always arrange for two things to be multiplied together by doing this. Now it's two things multiplied together. And so I could call them fg, and they're going to become f times g minus the integral of fg. The only issue is that one of these has to have a dash here and the other one has to have a dash here. So how am I going to do that? All right, well, if this one had the dash here, it would have to get integrated to figure out what g is, and I don't know what the integral of ln x is. So it has to be the one that I differentiate. So the other one has to be the one that has that I integrate. And that's how I made the decision. So f dashed is 1. I'm going to break my rules and just do it the way it's written. And g is that. So to figure out what f without the dash is, I'm going to have to integrate. So that's going to be x. The integral of 1 is x. And to figure out what g dash is, I have to differentiate. That's 1 over x. So this was an integral. This was a differentiation.
David?
Yep.
If you happen to have ln x plus 1,
Here,
yeah, would your differentiation still be 1 on x?
well, let's do it. So same deal would happen if it was x plus 1, but the derivative wouldn't be 1 on x anymore. So I'd be using the chain rule there. If it was an x, it would be 1 over x, but it's not an x, it's an x plus 1. And then I'd have to multiply by the derivative of this. And so I'd end up with 1 over x plus 1.
Right, yeah, yeah.
Well, that's what the problem is now. So that was what these things are. So the f is x, the g is still ln x plus 1, the f is still x, and the g dashed is 1 over x plus 1, which is sad because I don't know how to integrate that. So you'll notice that if this had been an x just here, then we would have had x times 1 over x, which would have been a 1.
Right. Yeah.
And I know how to integrate 1. So that's really cool. This would make a really nice exam question, actually, because now I have to integrate x over x plus 1, which isn't going to simplify. But I could use substitution for it. Let's do it. So then du on dx is 1. So du is dx. And also x is, so u minus 1 is x. And so therefore my integral becomes, oh, this is bad grammar. I need to just say what the original thing was so that we can keep track of the, so my integral becomes this now. So the x is now u minus 1. This is a 1 over u. That's a du. So I've got x ln x plus 1 minus the integral of u times 1 over u is 1, and minus 1 over u. So x ln x plus 1 minus, so the integral of 1 is u. The integral of 1 over u is ln the absolute value of u. And we're good. Now, what was u again? X plus 1. There we go. Not pretty, but there it is. Interestingly, this one doesn't have an absolute value and this one does, because this one was part of the original function and this one came about because of the integral. So there you go. So that wasn't the one I was planning to do. The one I was planning to do was just ln x, which would have had a 1 here, and so wouldn't have had this second bit. But it is possible to combine integration by parts and substitution. And in fact, it probably would have been a good idea for me to do substitution from the start, because you're supposed to do substitution first. So yeah. So I could have done the u first and then done the integration by parts. Yeah. which integral are you talking about, Eric?
Oh, sorry, yeah, you answered it in the end there.
Ah.
I did have a sort of related query regarding that,
Yep.
with similar sort of integrals, like 1 over x plus 1 or something.
Yep.
I think I have trouble determining when it becomes the natural log. I do recall something where if the numerator is the derivative of the denominator, then it's the natural log of that.
Yeah, I mean, that's the classic. So I'll just talk that through. So this one here, for example, if it was just 1 over x, it would be ln x.
Yep.
But it's not an x, it's an x plus 1. So we're in that situation where we would know what to do if it's an x, but instead it's like a constant times x plus constant.
Mm-hmm.
So that means that if it was just an x, it would be ln of x. But it's not an x, it's an x plus 1. And the derivative of this is a constant, so I can divide by that constant.
Yeah, right. So if it was 2 over x plus 1, would that still work? Or?
Yep. 2 over x plus 1. Well, it's technically this. 2 times 1 over x plus 1.
Okay.
And so I'd have 2 lots of ln of x plus 1. That's how I think about it.
Yep.
You can always move a constant off the top of a fraction if you need to.
Yeah, I think I get you. Yep.
Yeah. But what you were saying, and I've run out of paper, so we're switching to yellow because that's what I've got. You were saying, yes, there is a classic situation, something like that, where if the top is the derivative of the bottom, then you end up with an ln. But I have trouble remembering that rule, but I can do substitution. I can look at this and go, just a second, there's 2 things that are annoying here. The fact that there's a 2x on the top and the fact that there's an x squared plus 1 on the bottom. I would definitely not know what to do if there was an x squared plus 1 on the bottom, unless you haven't done inverse trig integrals, have you? Don't think you have.
I'm not sure. I can't
Yeah,
recall.
that's all right. I think that's in Maths 1A. But I can just attempt to make the most annoying thing u. And the thing on the bottom of the fraction is always the most annoying. So if u is that, then du on dx is 2x. And then du is 2x dx. And so this thing here, that's du. And so my integral becomes the 2x dx is the same as a 1 du. And you end up with that, because the bottom is u.
Okay.
So if you're experienced with this sort of thing, then you can start to notice that when the derivative of the bottom is on the top, it'll always end up being a 1 on u. Because it'll always have this trick will happen, and that whole thing will become du every time if the top is already the derivative of the bottom. So lots of people know that rule. And for an exam, it might be shave a couple of seconds off your working. Yeah. But if this had been like a 12x, then that would have been a little harder, because you would have had to move the 6 that's part of it out of the way. So if that had been a 12x, I would have seen this 2x, and then I would have gone, oh crap, that's like a 6 du is 12x dx, and now they match. Like that.
Yep. Cool. Thanks for that.
You're welcome. I'm going to have to finish because I have other students to talk to today. If you want to keep talking, then the virtual Maths Learning Centre is still open. So you can jump in there and keep chatting to people. But I have to go. So thank you for being here. And I wish you, whoa, sorry. I wish you clear thinking and calm nerves for your exam. See ya.